So in this video, we're going to be looking at stereoisomerism, but in our complex ions rather than organic compounds itself. Now, stereoisomers, you need to know, of course, they're going to be compounds with the same structural formula, but with a different arrangement of atoms in space itself. Now, in terms of stereoisomerism, in transition metal chemistry, one type is that, of course, you can get cis and trans stereoisomerism, where you end up with, of course, a cis isomer when you've got two ligands that are going to be at 90 degrees to each other, and a trans isomer where you can end up with two ligands that are going to be at 180 degrees to each other. Now, this only happens in octahedral and square planar complexes where we've got two different monodentate ligands itself. Now, of course, the top right example over here, you can see I've got cis and trans platinum. In the case of both of these, we can look at it in terms of ammonia or chlorine. I'm going to look at it in terms of the ammonia ligands. I can see that my ammonia ligands, they're going to be, of course, 90 degrees to each other over here in the cis isomer. And then if I were to look at my ammonia ligands over here, they're going to be 180 degrees from each other in my trans isomer itself. If I were to look at my octahedral complexes, you can see that I've got my trans isomer and cis isomer, where my chlorine ligands, they're going to be the two monodentate ligands that are different compared to the rest. In this case, for my trans isomer, they're going to be 180 degrees from each other, and then in my cis isomer, they're going to be 90 degrees from each other itself as well. Now, of course, I've got here another example where I've got two monodentate ligands versus the two bidentate ligands. You can see over here I've got my trans isomer because I've got 180 degrees between the ammonias, and then over here it's going to be my cis isomer because I've got 90 degrees between the two ammonias again. So yeah, there's our two different examples that we can get. Just be aware that, of course, you can end up with cis isomerism as long as they're next to each other. It could be over here and here, over there and there, or even here and here itself as well. Could be anywhere really. They just have to be 90 degrees from each other as well. So yeah, if we were to move on, I've got tasks for you to do. Feel free to pause the video, have a go at the following, and resume once you're ready to move on. So you're looking at these then, of course, I'm going to look at my two monodentate ligands that are going to be different. In this case over here, I can see that I've got 180 degrees between my two chlorines. So I know it's going to be, of course, in this case, a trans isomer. So we say trans, normally put labels on these every time we draw them, trans, and then it's going to be 180 degrees. Look at the next one. I can see quite clearly my chlorines are going to be 90 degrees from each other. They're next to each other. So I know this one's going to be cis, and so it's going to be 90 degrees itself. Look at the next one, right? My ammonias here are going to be different. They're going to be 90 degrees from each other, so we know, of course, they're going to be cis again. Looking at the next one, right, we can't actually end up with any isomerism over here because, of course, we've got our cyanides as the only ligand. We need to have at least two different ones that are going to be, of course, two chlorines or two ammonias or something like that to have cis and trans isomerism. Looking at E, right, if we were to look at this one, we've got 180 degrees over here. So we know, of course, we're going to end up with a trans isomer again. And the reason why is because our chlorine ligands, they're going to be 180 degrees from each other. If I were to look at the next one, right, I've got cyanide everywhere. Again, we can't actually end up with cis and trans isomerism because we need to have, of course, two different monodentate ligands at least. If we were to look at G, right, I've got here my cis isomer because, of course, I end up with 90 degrees. They're next to each other. So in that case, I say cis, and then my bond angle is 90 degrees. And then looking at H over here, I can see my chlorines are going to be 180 degrees. Could look at it in terms of ammonia as well. But we know, of course, this one's going to be trans. And so the reason why is because the two of the same ligand, they're going to be 180 degrees from each other. So moving on then, there's a bit of theory that we need to be aware of when it comes to an example or use of a complex. And the actual isomer that we're interested in is cisplatin itself, which of course has your chlorine ligands that are going to be 90 degrees from each other, or your ammonias that are going to be 90 degrees from each other. We know, of course, cisplatin, you might have come across it at GCSE. We need to remember what cisplatin is used for. It's used as an anti-cancer drug, and if we were to look at transplatin, it's not going to be effective itself. Now, cisplatin, it works by binding to DNA of cancer cells, and it stops them from replicating itself as well. So again, a use that we need to remember of a complex. Moving on, if we were to look at our second type of stereoisomerism, we've got optical isomers. Now, optical isomers, they're going to be stereoisomers that are non-superimposable mirror images of each other. And if I were to look at a mirror image, right, all we're doing is we're taking a isomer and then just reflecting it just as you would in a mirror itself. When we talk about non-superimposable, what we're saying is if I were to grab one of these isomers, stick it on top of another, would I end up with the same thing? The answer would be no. Now, in order to find out if something actually has a optical isomer, you need to think about it. First of all, is going to be octahedral, because octahedral complexes, they're the only ones in the OCR A chemistry spec that have optical isomers. And does it also have at least 2 bidentate ligands itself? In this case, you can see over here with this example, I've got 3 bidentate ligands, the ethane 1,2-diamine ligands. And of course, to draw an optical isomer, all you do is of course you keep your wedged and dashed bonds where they are. So you've got cobalt, and then you've got a bond going up, bond going down, my dashed bond, which of course is going to be going away from us, one over here as well, and then my wedged bond here as well, and then here as well. Now all we're doing is we're imagining that we're looking into a mirror, of course, from left to right over here, and we're just going to reflect everything that we see, right? So essentially, just as we said before, we would have nitrogens all around, making sure our bonds go to our nitrogen, because our structure, we need to be able to draw it out properly. And then of course, anything over here that we can see that's going to be close to the mirror. Let's say if you were to look at a mirror, you would see your own face, you wouldn't see the back of your head. You would end up with the same thing on, of course, the isomer on the right hand side. So again, we draw our mirror line out, which is what I've done already over here, and then I'm going to combine this over here, so I end up with my ethane part there, and then of course my ethane part over here, and then I'm going to end up with my hydrogens there as well, and then my hydrogens here, just making sure my dative covalent bond comes from the actual nitrogen, and the nitrogen bonds to carbon itself. Don't forget this one over here. Same thing again, I end up with H2 and then H2 as well. So yeah, some square brackets, because of course it's still a complex, and then I'm going to end up with a 2+ charge itself. So yeah, that's how we actually draw our optical isomer. And of course I've got 2 optical isomer over here, 2 enantiomers. So yeah, if I were to look at the next one, I've got over here a bit more of a strange one, but again, I've got at least 2 bidentate ligands. The other 2 are going to be monodentate, and although we don't actually have a charge over here, right, it's going to be neutral, we still put square brackets around it just in case. So again, right, we're looking into the mirror in this direction over here, so we see our face, we don't see the back, and we end up with, again, cobalt. I'm going to draw in my wedged and dashed bonds very quickly. I end up with something that looks like this, and then we're going to see a chlorine in our mirror over here, and then we're going to see a nitrogen over here, and then we're going to have nitrogen here, nitrogen there, and then nitrogen over here, but then we also end up with a chlorine over here itself, because remember, you're looking into the mirror in this direction itself. So you see, again, if you were to look in the mirror, you would see, of course, your face, you wouldn't see the back of your head. That's not how mirrors work, it's a reflection, isn't it? So again, my nitrogens are going to be bonded by a bridge, so I end up with something that looks like this, and then looks like this as well, and then I end up with H2 there, H2 there, H2 over here, and then H2 over here itself. Now don't forget, you also need some square brackets, which looks like this, and of course it's going to be neutral, you don't actually have a charge on there itself. So yeah, just remember that if you're dealing with an octahedral complex and you've got at least 2 bidentate ligands, you will end up with, of course, optical isomers. But in this case, on the right over here, because we've got these 2 chlorines, the monodentate ligands, they're the same, but they're different to everything else. We've got here a cis isomer as well, which are 90 degrees from each other. And of course, the cis isomer can actually form an optical isomer, the trans isomer cannot. So you can end up with 3 different isomers for that one formula itself. So yeah, moving on then, feel free to have a go at the following task. You just asked to give the different types of isomers that you can get, draw them, and how many isomers can you actually get as well. So yeah, looking at this then, my central metal ion is going to be nickel in this case, and then I've got at least 2 bidentate ligands, at least 2 ethane 1,2-diamine ligands. So I know, of course, I've got 2 lots of those, and then 2 lots of chloride ligands as well. So I know in terms of the types of isomerism I can get is going to be, of course, optical and cis and trans as well. Now, to make life easier, what I like to do is, of course, take nickel again. I end up with line going up, line going down. I end up with, of course, my dashed bond, my wedged bond, another dashed bond over here, and then another wedged bond over here. And then of course I'm going to copy and paste this a couple of times, right? I'm going to do it 3 times because there's 3 isomers that I can actually get. Now if I were to look at it in terms of cis and trans first, I'm going to draw the trans because that's easier. I'm going to end up with, of course, chlorine at the top, chlorine at the bottom over here. They're 180 degrees from each other. And then I'm going to draw my nitrogens on there, nitrogens on there. And then I end up with, of course, a little bridge, the little ethane bridge. And then I end up with the H2s on there. Now, of course, overall here, we're not actually given our charge because it's going to be neutral overall. And so I end up with something that looks like this. This is going to be my trans isomer. Why? Because my chlorine ligands are 180 degrees from each other. Now, if I look at the other case, right, if I were to end up with a cis isomer, that cis isomer can actually form optical isomers. Because if I were to reflect this structure over here for my trans isomer, I would end up with the same thing. I wouldn't actually end up with an optical isomer. But yeah, there's our first one done there for 1 mark. If we were to look at our cis isomer, I would need to have these 2 chlorines next to each other like this, and then my nitrogens are going to be bonded over here as well for the remainder. And then I'm going to end up with my bridge, which looks like this, another one over here. Easier to draw it this way, and then don't forget your H2s itself as well. So yeah, you end up with something that looks like this. There is my cis isomer, and I'm going to end up with some square brackets again, we're going to say this one's cis. So yeah, there's our second one done. We've got cis and trans, but remember the cis one can actually form optical isomers. So I need to draw out my mirror line. So I end up with the following over here, and I'm going to label that and say that is a mirror. And then of course I'm going to end up reflecting everything that I see. So I've got chlorine pointing this way, and then I've got nitrogen here, nitrogen there, nitrogen there, nitrogen there, and chlorine over here itself. Of course, I'm going to end up with my bridges, bridge over here, and then my hydrogens, I need to add them on. Could have drawn this a bit better, but I guess it will do. And I end up with the following. And then, of course, I'm going to end up with my square brackets over here, square brackets over here, and then of course that is our optical isomer itself. So we've got 3 isomers in total. The cis isomer will always form the optical isomer, and there's our answer. It's going to be 3 itself. So yeah, moving on, feel free to pause the video and have a go at this multiple choice question. Which statements are going to be correct for the complex shown? Pause the video, have a go, resume once you're ready to move on. So yeah, looking at this then, right, we can see here we've got PT, and then we've got 2 lots of ammonia, 2 lots of chlorine. So we've got to think platin, right? We know, of course, the cisplatin isomer is going to be used as an anti-cancer drug. That's going to be true. So, of course, we know one of our answers is going to be A. Look at B. The bond angles are going to be 109.5. That's going to be false. The reason why is because it's going to be square planar, where of course you've got your dashed bonds this way, dashed bonds that way, wedged bond this way as well. It's flat. Remember, you only end up with a tetrahedral shape with a bond angle of 109.5 degrees if you've got 4 bulky ligands like iodide, bromide, and chloride. In this case, we don't have 4 in total. We've only got 2 bulky ligands, and so it won't actually be 109.5 degrees. So yeah, if I were to draw the rest of it out just for completion, I end up with something that looks like this. This is cisplatin, the one that's used as an anti-cancer drug, and it has a bond angle of 90 degrees itself. So yeah, there's that complex there. So yeah, in that case, if you were to look at C, does it have optical isomers? No, because it does not have at least 2 bidentate ligands on an octahedral complex. So the only correct answer is just going to be A in this case. So yeah, A is going to be the only correct answer.